OpenThoughts-Agent, Data Recipes for Agentic Models. That is the preprint we are dissecting today on AI paper slop. And this is from a massive coalition, UC Berkeley, Stanford, LAION, a bunch of others.
Yeah, a really heavy-hitting group.
Totally. And they basically just dropped a masterclass on how we actually train AI agents. So here is your rapid-fire summary, straight to the core insight. The secret to building broadly capable agents is not just, throwing more compute at the problem. It is highly systematic, almost obsessive data curation.
Right. Obsessive is the perfect word for it.
They open source this fully tested 6-stage SFT pipeline and a 100K dataset that produces OpenThinker Agent 32B, which beats models like Nematron Terminal 32B across 7 different benchmarks. So if you are an ML engineer listening right now, here are your immediate takeaways.
Get your notepads out for this one.
Seriously. First, your absolute smartest frontier model might actually be your worst teacher for fine-tuning. Second, keeping multi-turn trajectories, like 5 or more turns, matters vastly more than raw token volume. Third, you will hit a scaling plateau around 31,000 tasks, and synthetic augmentation is basically the only way through it.
Yep, the only way.
And finally, when you move to reinforcement learning, the specific data source you choose fundamentally alters the behavioral personality of your agent. Like, it programs it to either overexplore or ruthlessly compact its logic.
Which is just wild to think about.
Yeah.
But to give some broader context here, we need to talk about what I like to call the agentic data black box.
Oh, I like that term.
Yeah, I mean, it is arguably the defining gap in OpenAI research today. Because think about recent massive open weight releases like DeepSeek V4, right? You get a dense technical report, maybe a 50-page PDF detailing the architecture, the router mechanisms, the hardware clustering, all that. And then you get maybe like a single vague paragraph waving at the training data.
Literally just, we trained it on a high-quality, diverse data set, and that's it.
Exactly. The actual curation recipes, the exact mix, the filtering strategies, how they actually sort the data to elicit true agentic behavior, that remains entirely locked behind corporate doors. So what makes this release so critical is that this coalition actually built a pipeline. They ran over 100 controlled ablation experiments, and they published the exact recipes that work. Previous open efforts, like W. Smith or Susha, they mostly just focused on single benchmarks.
Right, which is cool, but limited. And they ran those ablations using an 8 billion parameter-based model, Qwen3BB, I think, to keep the compute budget manageable, right?
Yeah, testing 10,000 trajectory batches per ablation to see what actually moves the needle before scaling up.
Okay, so before we get into the pipeline itself, I want to look at how they define success. Because if their ultimate goal is to build general agents, agents that can theoretically do anything from booking a flight to navigating some horrible, complex web UI.
Which we all want, yeah.
Why do they focus their core evaluations almost entirely on software engineering and terminal tasks? It feels like, like they are building a highly specialized coding assistant rather than a general agent.
I get that critique, and it sounds narrow on the surface. But software engineering in terminal environments, like SWE-Bench Verified 100 or Terminal-Bench 2.0, they are the most unforgiving arenas we currently have for evaluating long-horizon reasoning.
Unforgiving how? Like just strict grading?
Well, think about what a terminal actually forces an agent to do. It has to maintain its state and its memory across dozens of sequential turns. It executes a command, it parses the raw, completely unstructured standard output, it has to realize it made a syntax error, recover from that error without hallucinating some weird fix, and then formulate a brand new plan.
Right, there's no graphic interface to hold its hand.
Exactly. If your agent can reliably navigate a sandboxed Linux terminal to resolve a complex multi-file GitHub issue, it has mastered a level of sequential reasoning, tool use, and state management that transfers beautifully to almost any other domain. It is basically the ultimate proxy for true agency.
I see. It's an environment where the agent simply cannot fake it. Like the code either compiles and passes the tests or it doesn't. And there's no partial credit for sounding confident.
Not at all.
Okay, so once you decide on the environment, you have to find the tasks to actually train the model on. That's stages 1 and 2 of their pipeline, sourcing and mixing. How much does where you source the data actually matter? Because if it is all just coding and terminal problems, isn't the data all functionally kind of similar?
Oh no, the variance is absolutely staggering. The source of your data can swing the final capability of the model by up to 30 percentage points on a benchmark like SWE-Bench.
30 points? Wait, really?
Yes. That is not a minor optimization, right? That is the difference between a state-of-the-art model and a totally useless one. They found that relying on a single source causes the model to overfit heavily to that specific formatting.
Oh, that makes sense.
Yeah, so the sweet spot they found is mixing the top 4 to 8 sources. Specifically, combining synthetic issue resolution datasets like SW-Smith with high-quality human-written infrastructure questions, like the ones you find on Stack Exchange for Superuser or Tezos. That yields the most robust baseline.
So you need a curated mix of very specific problems. But, okay, once you have that perfect mix of tasks, you need someone, or rather some model, to actually solve them to generate your training trajectories. This is stage 5, teacher selection. If I am setting up this pipeline today, my immediate instinct is to grab the absolute smartest, most powerful frontier model available via API and just have it generate all the answers, right?
And you wouldn't be alone in that. That is the assumption driving almost every post-training pipeline right now. Just use the biggest model you can afford.
But I'm guessing that's not what they found.
No, the ablations revealed something completely counterintuitive. They took their best mix of tasks and had several different frontier models act as the teacher to generate the solutions. They tested top-tier bleeding-edge proprietary models against slightly older open-weight models. So, for example, GPT 5.3 Codex versus GLM 4.7-AWQ.
Okay.
The bleeding-edge model, GPT 5.3 Codex, which objectively scores much higher on all these benchmarks when tested on its own, it was actually the worst teacher for the student model.
The worst teacher.
Yeah. The student trained on its data significantly underperformed. The student trained on the older, technically less capable model's data by like 5% on Terminal-Bench 2.0.
I love this because I like to call this the smart teacher fallacy.
Oh, tell me about that.
So imagine you hire the most brilliant principal engineer in the world, right? They're an absolute genius, but they refuse to comment their code and they write terrible documentation.
Oh, we all know that engineer.
Right. And why do they do that? Because their brain naturally skips over all the implicit steps. They look at a complex system architecture and jump straight from step A to step F.
Yep.
But then you have a solid mid-level engineer who meticulously comments every single step of their logic. They explicitly write out how to get from A to B, B to C, and so on. If you are trying to train a junior developer, or in this case, fine-tune a base model, you do not want the silent genius. You need the meticulous explainer.
That is a perfect analogy.
Yeah.
Mechanistically, that captures exactly what is happening during model distillation. An agentic trajectory is only useful as SFT data if the student model can clearly learn the causal link between the observation and the action.
Right, the chain of thought.
Exactly. If the teacher model is so capable that it internally jumps straight to the correct bash command without printing out a trail of intermediate thoughts or exploratory commands, or even, making and fixing small mistakes, the student model cannot learn the actual process of problem solving.
It's just seeing the final answer.
Right. The slightly older model, like GLM 4.7, might take longer to arrive at the solution, but it generates verbose, highly structured reasoning traces. It shows its work, which is exactly what the student needs to mimic.
Show your work. It's the oldest rule in math class, and it turns out it applies to LLMs too. I love that.
Yeah, it really does.
So we've got a meticulous teacher generating these verbose reasoning traces, but we can't just dump all of them into the training run. We have to filter, which gets us to stages 4 and 6. The researchers point out 2 major filtering strategies that actually move the needle. First, they look at all the responses and keep the ones where GPT-5 yielded the absolute longest responses.
Yeah, which improves performance by about 3 percentage points.
And second, they filter the actual agent rollouts to only keep trajectories that have a minimum of 5 distinct turns between the agent and the environment.
Which fundamentally changes the shape of the data the model is ingesting. You're stripping away the quick, easy wins entirely.
Okay, wait. I'm stuck on something here. If they're aggressively filtering for trajectories with 5 or more turns, isn't that just a massive confounder? By definition, longer multi-turn trajectories contain way more tokens.
Right, they are much longer documents.
So are we actually teaching the model better multi-turn reasoning, or is the model just getting smarter because we fed it a massively bloated textbook during SFT? If I feed a model 10 times the volume of data, of course it is going to perform better.
It totally looks like a cheat code, right? Any rigorous ML engineer looking at those results would immediately raise that exact critique. But the authors actually anticipated it.
Yeah.
And they designed a brilliant control experiment to isolate the variable.
Oh, nice. How did they do that?
They created a strict compute-controlled token budget. Let's say exactly 145 million tokens. They trained one model exclusively on the filtered dataset, the one restricted to complex trajectories of 5 or more turns, capping it right at that 145 million token limit. Then, they trained a second model on a completely random subsample of trajectories, but carefully matched it to hit that exact same 145 million token count.
So the sheer volume of data is mathematically identical between the two. The only difference is the shape of the interactions inside that data.
Precisely. And the model trained on the 5-turn minimum data still completely dominated. It won by 5.4 points on SWE-Bench and 3.8 points on Terminal-Bench.
Wow.
Yeah, this proves definitively that the structure of the data, specifically exposing the model to long-horizon, multi-turn interactions, matters much more than raw token volume. Because think about what a 5-turn trajectory actually contains.
It's not just a straight line to the answer.
Exactly. It contains failure. It contains the agent trying something on turn 2, getting a weird error message on turn 3, regrouping, analyzing the error, and pushing through to a solution on turn 5. A random assortment of short one-turn successes teaches the model absolutely nothing about resilience or state recovery.
That is a massive takeaway for anyone running a fine-tuning pipeline this week. Stop scraping the barrel just to hit an arbitrary token count. Focus on structural depth.
100%.
But let's talk about the reality of scaling. Because eventually, if you want a frontier-class model, you do need more data. The authors take all these ablation insights, the right mix, the meticulous teacher, the structural filtering, and they try to scale up. They want to move from their 10,000 trajectory test batches to a massive 100,000 trajectory dataset to train their final 32 billion parameter model. And they hit a brick wall.
The dreaded scaling plateau.
Yeah?
Yeah, they initially tried the most straightforward approach, right? Just generate more rollouts per task. Like, if a task description asks how to configure a specific network protocol, just have the teacher model solve it a few different ways.
Right, just run it again.
But once the data set grew past roughly 31,600 examples, performance simply flatlined. The model stopped getting smarter, regardless of how many extra rollouts they shoved into the pipeline.
Okay, if you are an ML engineer staring at that plateau, your first instinct is probably to just go find more task sources. If the top 4 sources gave you 31,000 good tasks, why not just scrape the top 16 sources to get to 100,000?
Because the quality drop-off in agentic data sets is a cliff, not a slope. They actually tested expanding the source list. As you move down the quality tier, you introduce noise, poorly formatted environments, and highly ambiguous success criteria.
So it's not just unhelpful, it's actually harmful.
Very harmful. Incorporating those lower-tier sources actively degraded the model's performance on every single benchmark. Adding bad data doesn't just fail to help, it actively overwrites the good behaviors the model learned from the high-quality data.
Okay, so you are tracked. You can't just generate more answers for the same questions because the model overfits and stops learning. And you can't just scrape worse questions because the noise ruins the model's reasoning capabilities. What is the actual bottleneck here?
The bottleneck is task description diversity. Let's look at one of their best sources, the Stack Exchange Tezos dataset. It only contains 997 unique problems.
That's tiny.
Exactly. If you show a student model those exact same 997 prompts over and over, it learns the semantic structure of those specific paragraphs, not the underlying logic required to solve them. The breakthrough, what we can call the synthetic fix, was to use a language model to synthetically augment the instructions themselves.
Walk me through exactly how that works in practice. How do you augment an instruction without fundamentally changing the underlying problem or breaking the environment?
Sure. So imagine the original prompt in your dataset is, write a Python script to parse this specific JSON file, extract the user IDs, and handle any missing keys. The underlying logic required to solve that is file I/O, JSON parsing, and basic error handling.
Right.
A synthetic augmentation would tell an LLM, rewrite this prompt, change the scenario, change the tone, and change the surface constraints, but keep the core technical requirements absolutely identical.
Oh, I see.
So the new augmented prompt might be, you are a database administrator dealing with a corrupted system log formatted as JSON. Write a recovery script that extracts all the user IDs while gracefully skipping any corrupted entries.
That is a great way to visualize it. You keep the skeleton of the problem entirely intact, but you change the skin. You're putting different costumes on the exact same underlying logic puzzle.
That is exactly it. They took those 997 base problems and exploded them into over 21,000 distinct, synthetically varied surface forms. The core technical requirements remain the same, so the terminal environment could still automatically verify if the solution worked, but the model had to learn to recognize and solve those requirements regardless of how they were phrased.
So by artificially inflating the surface level diversity, they completely shattered that 31,000 example plateau.
Yep, broke right through it.
They successfully scaled the dataset to 100,000 high-quality tasks, making the OpenThoughts-Agent v2 dataset. And the resulting model, OpenThinker-Agent 32B, it punches so far above its weight class. It achieved an average accuracy of 44.8% across 7 benchmarks, including out-of-distribution ones like MedAgent-Bench and Finance-Agent Terminal.
Which is incredibly impressive for a 32B model.
Right. Trained entirely on this curated open source recipe, it comfortably outperformed the previous open data SOTA, Nemotron Terminal 32B, which scored 40.9%. It establishes a real David versus Goliath dynamic, proving that rigorous, clever data engineering can beat raw compute scale.
It really is a masterclass in SFT data curation.
Yeah.
But what makes this paper a landmark is that they don't stop at supervised fine-tuning. They push into the final phase of post-training, which is reinforcement learning.
Oh, the RL phase? This is where things usually get weird.
Extremely weird. Because of massive compute constraints, they actually shift down to an 8 billion parameter scale here, using an algorithm called RLO reinforcement learning with leave one out. It's a specific RL setup used to establish a strong baseline. The core question they wanted to answer was, does the data source matter as much in reinforcement learning as it does in SFT?
And the variance here is just as extreme, right? They ran controlled ablations where the RL algorithm and hyperparameters were identical, but they swapped out the data source used to generate the rewards.
Yeah, and the clear winner was a data set called PyMethods2Test.
PyMethods2Test. What is that exactly?
This is essentially a collection of competitive programming problems recast as Python contracts. Using this specific source for RL resulted in a massive performance spike over the SFT baseline. I'm talking plus 5.4 points on SWE-Bench Verified.
Okay, I have to throw a flag here. Whenever I see a massive performance spike in an RL agent, especially on agent benchmarks, my reward hacking alarm starts ringing loudly.
Oh, absolutely.
We have all seen models that figure out how to game the verifier. Did the model actually get smarter, or did it just learn some formatting trick to spam the mark complete tool and trick the environment into giving it a high score without actually solving the problem?
It's entirely rational to be suspicious of huge RL gains, because models are notoriously lazy. But the researchers conducted a fascinating mechanistic analysis of the agent's behavior before and after the RL phase. They dug into the telemetry to prove it wasn't taking shortcuts.
So what did the logs show?
When trained on this Python contract dataset, the agent developed a legitimate exploration policy. The internal logs are wild. The number of think tokens, the internal monologue where the model plans its next move.
Right, the chain of thought before it acts.
Yeah, that increased by 116%.
Wow, so it's thinking way more.
Way more. And the frequency of self-correction phrases, where the model explicitly realizes a mistake and pivots, that shot up by 81%. Tool calls increased by 31%. It was literally working harder, thinking longer, and trying more complex sequences of tools.
But wait, if it is using tools more often and trying way more things, isn't it also failing more often? Like, did the tool error rate go up?
That's the key question. The absolute number of errors increased, yes, because it was executing far more commands. But the error rate, the percentage of actions that resulted into failure, that only rose by 4.1%.
Oh, okay, so it's not just flailing around wildly.
Exactly. The model didn't lose its core competence or degrade. It just became incredibly tenacious. It learned to thoroughly explore search space, hit dead ends, and use that massive increase in self-correction capability to recover.
That is fascinating. It basically learned grit from competitive programming. But what happens if you use a completely different data set for the RL phase? Does it still learn grit?
This is where the findings get profound. They ran the exact same RL pipeline using a completely different data set, Elm Verifier Freelancer, which focuses on broad, general-purpose tool use. The resulting agent developed the complete opposite behavioral profile.
The opposite. How so?
Instead of exploring, it learned to ruthlessly compact its logic. Its think tokens fell by 42%.
Yeah.
Its self-correction fell by 59%. It optimized for fast, hyper-efficient execution.
I think I need an analogy here to ground this. It sounds like you are training pilots, but using two totally different environments.
Okay, I like where this is going.
Like, the Python contract dataset is like a flight simulator. Crashes are free, the puzzles are brutal, and the only way to succeed is to methodically test every dial, fail 100 times, and truly learn the physics of the plane. So the RL algorithm creates a pilot who is an exhaustive explorer.
Yes.
But the general tool use data set, the freelancer one, is like live combat. If you hesitate, if you dither around exploring options and self-correcting, you get shot down or the system times out. So the RL algorithm creates a pilot who makes hyper-fast, compact, decisive actions.
That captures the dynamic perfectly. The reinforcement learning data source isn't just imparting factual knowledge. It is fundamentally programming the agent's behavioral personality. You are explicitly choosing whether your agent approaches problems as a methodical explorer or a ruthless executor based entirely on the environment you expose it to.
That is huge. So if you are an ML practitioner listening right now, looking at your own post-training pipeline this week, here is your actionable checklist based on this blueprint. Number 1, go find the meticulous explainer model to generate your traces, not the silent genius. Number 2, stop optimizing for raw token counts and start filtering your SFT data for multi-turn structural depth, 5 turns or more.
Minimum.
Right. Number 3, when you inevitably hit a task diversity plateau around 30,000 examples, use synthetic augmentation to rewrite the surface forms of your prompts. And number 4, be incredibly deliberate with your RL data sources. Because you aren't just teaching a skill, you are hard-coding a personality.
The implications for that last point are what I really want to leave everyone with today to, mull over. If training on a flight simulator locks a model into exhaustive exploration and training in live combat locks it into hypercompaction, well, how do we design the next generation of data sets? How do we build an RL curriculum that teaches an agent when to dynamically shift between these strategies rather than statically locking one personality in?
Oh, an agent that knows exactly when to be the patient, exhaustive scientist and when to be the decisive, ruthless executor. That is the billion-dollar question for the next frontier of AI. Thanks for joining us in the Agentic Data Black Box. We'll catch you next time on AI Paper Slop.